When we use recombinant frequency to measure distance, we assume that recombinant frequency and distance are linearly related. In fact, they are identical to each other. So if you have a recombinant frequency of 0.05, then your distance between genes is 0.05. If it is 0.2, if you measure a recombinant frequency of 0.2, then the distance is 0.2. And if you measure a recombinant frequency of 0.5, then the distance is 0.5. And so we have this straight diagonal line, which we assume maps the recombinant frequency to distance. However, there is a problem with this idea. And in order to illustrate this idea, I have three sort of pairs of genes located at various distances from 0.05 to 0.2 to 0.5 map units. And in the first pair of genes, we know that the probability of crossover is 0.05, and so the recombinance, the percentage recombinance, the recombinant frequency that we're going to see is also about 0.05. Now, when we look at the second pair of genes that are separated by a distance of 0.2 map units, then the probability of having a crossover, and therefore the probability of seeing recombinance, is 0.2. However, we know that a double crossover is also possible, and if you have a double crossover, then you do not get recombinant genotypes when you're looking at a pair of genes. Therefore, the actual recombinant frequency we will observe is going to be the probability of crossover minus the probability of double crossover, which is, by the product rule, 0.04. And therefore, a corrected crossover probability is going to be 0.16. Now, this is not entirely accurate, because even though we are taking into account double crossovers, triple and quadruple and even more crossovers are possible. However, this is a pretty good approximation, because the probability of triple crossovers is going to be 0.2 cube or 0.008. So it's going to be pretty small, and it's safe to neglect it. So now, instead of observing a recombinant frequency of 0.2 as expected by the green line and our assumptions based on which we measure distance using recombinant frequency, I'm actually going to see a recombinant frequency that's slightly less than expected. We can do a similar exercise for the third pair of genes, where the probability of crossover is 0.5, and the probability of a double crossover is going to be, by the product rule, 0.5 square, or it's going to be 0.25. And therefore, if I correct my the proportion of recombinance I'm going to get about 0.25 recombinance, because of the large amount or the large probability of double crossovers. And therefore, instead of observing a recombinant frequency of 0.5 based on our assumptions, we're going to see a much smaller recombinant frequency. So even though our assumption based on which we compute distance using recombinant frequency is the green line, in reality the recombinant frequency does not behave in that linear manner, but it actually saturates, so that when genes are separated by large distances, it does not lead to a proportional increase in recombinant frequency. And our estimates about the distance between genes are, in fact, overestimates. And so instead of using the green function, so normally what we do when we measure distance using recombinant frequency is that we measure some recombinant frequency and then we use that number to translate it into a map distance using that green straight line. If in fact we want to do a more accurate estimation of distance, instead of using this green line, we can use this purple curve, and it will give us a much better estimate of the distance between genes from recombinant frequency, because it will not in fact be underestimating the distances between the two genes. And this purple curve is known as the mapping function. But before we get into the details of the mapping function, let us review what fraction of gametes are recombinant in a given meiosis. So if you have a 0 crossovers, no crossover has occurred, then evidently there are no recombinants in a given meiosis. If you have one crossover, then you have 50% recombinants. The two non-sister chromatids that undergo crossover will be recombinant, while the two non-sister chromatids that did not participate in the crossover will be parental, and this will be always true for one crossover. Interestingly, it turns out that even if you have two crossovers, a double crossover, on average you will produce 50% recombinant gametes. So if you have two-strand double crossovers, so you have two strands had a crossover and then the same two strands crossover a second time, then there are no recombinants produced. If you have a double crossover that involves all four strands, so these two non-sister chromatids crossed over and then these two non-sister chromatids also crossed over, then you will end up with 100% recombinant gametes. If you have a double crossover that involves three strands, then you will end up with 50% recombinant gametes. So even though the number of recombinant gametes is different depending on whether the double crossover involved 2 strands, 4 strands, or 3 strands. On average, if you take all 4 together, you have 0 plus 4 plus 2 plus 2 divided by 16, which is 8 over 16, or 50% recombinance. As it turns out, on average, if there are 1 or more crossovers, then 50% of the gametes are going to be recombinant. Next, let us write down the mapping function, visualize it, and use it to compute corrected map distances. Let M be the average number of crossovers between 2 genes. The first step in writing down the mapping function is to determine what is the probability of no crossover between 2 genes as a function of M. So we can do this visually. Here I have a plot where on the x-axis I have M, the average number of crossovers, and on the y-axis I have the probability P of no crossover. Evidently, if the 2 genes are very close, that means that the probability of the average number of crossovers between the 2 genes is really small. So let's say here, then the probability of having no crossovers is going to be very high. However, as you increase the distance between 2 genes, and therefore as you increase the average number of crossovers between 2 genes, so let's say here, the probability of having no crossovers is going to be low, because the farther apart 2 genes are, the greater the chance that there will be a crossover. And if you do the math, you can work out that this function, which is the probability of no crossovers, is actually e to the power minus m. It's an exponential decay. In step 2, we say, what is the probability of at least 1 crossover, or 1 or more crossovers? And since the probability of no crossovers is e to the power minus m, the probability of at least 1 crossover is going to be 1 minus e to the power m. And in step 3, we use this expression to determine what the recombinant frequency should be. So the probability of having at least 1 crossover tells us how many meioses have had a crossover. And since recombinant frequency is on average 50%, so 50% of the gametes are recombinant, therefore the recombinant frequency is going to be 50% of the probability of having at least 1 crossover, and so it's going to be half times 1 minus e to the power minus m. and we can plot this. First, I'm going to make some space. If you plot this mapping function, where on the x-axis you have m, the average number of crossovers, and on the y-axis you have measured recombinant frequency, this function looks very much like the function we plotted. And one interesting thing is that as m goes to infinity, that means the genes grow farther and farther apart, e to the power minus m goes to 0 because it's an exponential decay, and therefore the recombinant frequency goes to half. And that makes perfect sense, because if two genes are unlinked, then the recombinant frequency is 50%, and therefore it's impossible for linked genes to have a higher recombinant frequency than two unlinked genes. So now that we have the mapping function, the procedure for determining the corrected map distance is to take the recombinant frequency that was measured in a test cross, and we know that if we just use that recombinant frequency unmodified, that is an underestimate of the distance between two genes, and therefore we can use that recombinant frequency to determine what is the average number of crossovers between those two genes using the mapping function. Effectively, we are solving for m. And once we have determined m, which is the average number of crossovers, we need to translate back into map units. And so we have to translate back to recombinant frequency. Since we know that on average, every meiosis produces 50% recombinant gametes, if you have m average crossovers, you will end up with m over 2 recombinants, and that would give us the corrected map distance. Next, let us practice this with an example problem. And in this problem, it's from Drosophila. We have 3 linked genes: vermilion, cut, and crossveinless, and the recombinant frequency between vermilion and crossveinless is 18.5%, whereas the recombinant frequency between cut and crossveinless is 6.4%, and our goal is to determine the corrected map distance, because these distances are in fact underestimates of the true distances between the genes. And so we will use our strategy to solve for m. So if I make a plot of m and recombinant frequency, it's gonna be something like this, and the recombinant frequency here is 18.5% or 0.185, and we have to find what is the corresponding m. And so 0.185 is equal to half 1 minus e to the power m, and we have to solve this equation. And as a first step, we can multiply both sides by 2, giving us 0.37 is equal to, the 2's cancel, 1 minus e to the power minus m. And then we can subtract 1 from both sides, giving us negative 0.63 on the left side and negative e to the power minus m on the right hand side. And we can multiply both sides by negative 1, giving us e to the power minus m is equal to 0.63. And if we take log of both sides, we get negative m is equal to, and you would need a calculator to check this value, and the log of 0.63 is negative 0.46, and we can multiply both sides by negative 1 to get m is equal to 0.46. Now, this is just the average number of crossovers, but if we want the corrected map distance, we have to go back to recombinant frequency. And since on average 50% of gametes are recombinant, we would get a recombinant frequency or a corrected map distance of 0.23 or 23 map units, which is much more than the measured recombinant frequency of 18.5, and it shows how the recombinant frequency on its own underestimates the map distance. And so this m here is 0.46, which translates to a map distance of 0.23. And we can repeat this exercise for the distance between cut and cross veinless. I'm going to make some space here first. And let's see. So my recombinant frequency is 0.064 in decimals, which is equal to a half 1 minus e to the power minus m. And so we are solving for m, and once again multiplying by 2 on both sides, we get 0.128 is equal to 1 minus e to the power minus m. And subtracting 1 from both sides, we get negative 0.872 is equal to negative e to the power minus m. We can multiply both sides by -1 to get e to the power negative m is equal to 0.872. Taking log of both sides, we get negative m is equal to log of 0.872. And that gives us negative m is equal to negative 0.1370, and that implies that m is 0.137, and the corrected map distance is half of that, or 0.137 by 2, which is equal to 0.068, which is actually very close to the original map distance. And this shows that when the recombinant frequency is low, then the map function is approximately linear. It resembles a straight line, and therefore the uncorrected map distance is fairly accurate by itself. One more thing that we can do here is determine what is the probability of no crossover between, let's say, vermilion and cross-veinless, and we know that the probability of no crossover is equal to e to the power minus m, which in the case of vermilion and cross-veinless, if you look over here, is equal to 0.63. To summarize, we started by recognizing a problem with map distance, which is that map distances underestimate the true distance between genes because they do not account for double, triple, quadruple, and so on crossovers. We came up with an approach called the map distance, which takes into account these multiple crossovers and gives us an accurate estimation of the map distance. And the way we apply the mapping function is to determine the average number of crossovers m from the measured recombinant frequency by solving the equation for m. And then once we have the m, we divide it by 2 in order to get the corrected map distance. And we do this because on average 50% recombinant gametes are produced per meiosis.